We know that the frozen phonon method allows calculating um, vibrations only at k points which are not too close to the gamma point. There is a method suggested in that paper first that allows calculating um, phonons at any k point using just the primitive unit cell. So here I will describe the main idea of that method. I won't go into great details. If you are interested, you will have to consult the actual literature. There's a lot of it. We will start from Concham equations, which are written here. Phi are Concham orbitals, epsilon is the Concham energy, and T is the kinetic energy operator, and G is an operator associated with the Hartree interaction, Hartree term, interaction of electrons with nuclei, and exchange correlation potential. And this G operator can also be written as a functional derivative with respect to electronic density ρ of the energies of these three energies: the Hartree energy, exchange correlation energy, and interaction of electrons with nuclei. The total energy of the system contains these three terms: Hartree, exchange correlation, interaction of electrons with nuclei, but also nuclear interaction term, which is explicit in atomic displacements, and the contribution from the kinetic energy of the electrons. And phi, as I said, are Concham orbitals, and electronic density is given as usual in the Concham picture as a sum of squares of Concham orbitals summed over all occupied states. The first derivative of the total energy with respect to atomic positions is trivial and is given by the Hellman-Feynman theorem. And this theorem states that the first derivative of the energy with respect to atomic positions is given by two terms. The first one contains the derivative of the electron-nuclear interaction with respect to atomic positions integrated with the electronic density. The contribution due to electronic density, because it changes, of course, when atoms are shifted, cancels out in the first derivative. This is the core of the Hellman-Feynman theorem. And there is a second term in which we have to differentiate the nuclear-nuclear interaction, which is a simple one because the nuclear interaction is just a Coulomb interaction between nuclei. It is given explicitly. What we're interested in here is in the second derivative of the total energy with respect to atomic displacements, which I use xi, Greek letter here for simplicity. So what we need to do is to differentiate this expression with respect to xi prime. If xi was this R A alpha, A is the atom, alpha is Cartesian coordinate. So we call it xi for brevity. Yeah. So the second derivative will be given by differentiation of the nuclear-nuclear interaction, which is easy. Then we can differentiate this term, which is also easy because the nuclear electron interaction is also written explicitly with respect to atomic positions. So this is here written. But there will be also the third term in which we will have to differentiate the electronic density. So this is the term which is not easy. So we need to find a way to calculate this term as well. In order to do this, let's assume that we have a change of atomic position from some to some other. So this is a little change, delta xi. Once we change the atomic positions, the electronic density would respond. This electronic density is composed of Concham orbitals, which satisfy the Concham equation. So if G changes, um, it will, because G depends on atomic positions, then the orbitals would change, and this would cause the change of the electronic density, which will be self-consistent, of course. So that change of G is due to changes of these three operators. So electron-nuclear interaction is easy to calculate when the atoms move because it's explicit. But these two terms, they depend on the electronic density as functionals. So in order to calculate the change of these two due to the change of electronic density, uh, we need to use this functional derivative chain rule. So we differentiate this to values with respect to electronic density change, and we multiply by the change of electronic density. So this functional derivative can actually be easily calculated. First of all, the Hartree potential is given explicitly, and its derivative would give us simply the Coulomb interaction potential. The exchange correlation potential, if differentiated with respect to electronic density in the LDA approximation, is a local term which contains the derivative of the whatever functional is used for exchange correlation with respect to electronic density. Therefore, if we take a derivative now of G with respect to some change of delta C prime, then we simply divide this expression by this delta C prime, and we arrive at this formula, in which here we have a derivative of electron-nuclear interaction, which is explicit. This term would give us an integral of the Coulomb interaction and derivative of the electronic density with respect to atomic positions. And this second term, exchange correlation term, because of the delta function, becomes local. There's no integral. But it also contains the derivative of electronic density with respect to atomic positions. So, if atomic position changes, that causes a change in the G operator entering the Koncham equation. And the change of this operator, its derivative with respect to this atomic position, can be calculated like that, but it requires, because of the self-consistency, to know the change of the electronic density due to this change of atomic position. So we need to devise a way to calculate this change. Of course, the electronic density is given by that expression, and therefore the change of the electronic density can be written explicitly via the changes of the Koncham orbitals. The orbitals, they satisfy the Koncham equation. Therefore, if G changes by something, this can be considered as a perturbation. And of course, we assume that this perturbation is very small, because this is what happens when you calculate the derivatives. In the calculating the derivatives, you have an infinitesimal change of the variable. So the change of G is small, and we can use first order perturbation theory to calculate the change of the orbitals, the solutions of this equation. And as you can see, that change is given as a linear combination over all orbitals, Koncham orbitals, and with some not only over occupied orbitals, but over all orbitals, occupied and unoccupied as well. Here we have the changes of Koncham energies, but in the numerator we have the matrix element between orbitals of the change of the G operator. And this formula allows us to calculate the derivative of the orbital with respect to C, the change of the atomic position. And you can see, if you calculate the derivative of that term, you divide it by delta C prime, you divide delta G by delta C prime as well. So you will have here a derivative of the G, which we had before here as calculated by the derivative of rho. So now these two equations can be combined together. So the derivative of rho calculated from here and from here appears to be given by that expression, and it is related to the derivative of G. At the same time, derivative of G is related to the derivative of rho. So we have a set of two self-consistent equations, which one should solve, and once this is done, that derivative is established, and once this derivative is established, you have this third term available to you, and you can calculate the Hessian. And nowhere in this case we needed an extended unit cell. We can use just a primitive unit cell for that calculation. Of course, this calculation is self-consistent and requires summation over all orbitals, not only over occupied orbitals. So we have a double sum here for over occupied and unoccupied orbitals. V stands for valence band and C stands for the conduction band, but it's just a formal assignment here. So advantages of this method are that any K point becomes accessible. Um, One can simplify calculations by using symmetry. There's an efficient implementations exist of that method in various code, Quantum Expressor, VASP, Abonit, and so on.